In this lesson, we're going to examine some other types of regression, namely those that are nonlinear. Not all relationships are a linear relation. They don't all have a correlation that goes up and to the right or down to the right. Just because one thing increases doesn't necessarily mean the other things increase. There are a number of other types of models we can examine, including things like exponential growth, ones that go up, or exponential decay. We could look at old things like quadratics that go down then up, or up then down. We could talk about cubic things. We could talk about quartic things. There's all different kinds of nonlinear models. And that's really what we spent the rest of our high school experience developing, is equations that represent nonlinear things. Like the linear regression, however, there's many things our calculator can do. It can do all of these functions. We just have to learn how to use it. Okay? Here, because we're looking at nonlinear models, we're not going to look at the correlation coefficient anymore. Instead, we're going to look at the coefficient of determination, and it's called r squared. It doesn't have a sign. It's only a positive number because nonlinear functions, as you can see in the pictures, don't go up or down. They go both directions. But like r, the closer you are to 1, the better the dots fit the curve of best fit. And notice I said they're curve of best fit as opposed to line of best fit. So let's take a look at an example here. Again, use your graphing calculators. And clear the memory, turn your stat diagnostics on. Right, so remember, under mode, we're going to go to the bottom, so go up over the top, turn diagnostics on. It won't affect anything else in your calculator, but you need that on in order to find r, and in this case, r squared. Okay, our example is looking at the growth of bacteria. Okay, this is an example we've talked about in grade 11. Okay, we know what kind of shape it probably is going to fit. We're just going to look how to do it with a graphing calculator. What do we do first? We got to enter our stats, right? So stat, edit, let's put our data in. Okay, so L1, go over to L2. Check your numbers, make sure you got them all right. Oh, I messed one up, so 320, 168, 82, 43, 21, and 10. Okay. We're going to create our scatter plot. Second, stat plot. Got to turn it on. It's doing what we want it to, which is a scatter plot. So we can press zoom 9. Okay, let's classify our linear correlation. So if you were to look at that, does that look like a linear correlation? I don't think so. I don't think it looks linear at all, really. But if we were to draw a line of best fit, it would definitely be positive. And, well, some of the dots would be above it, some of the dots would be below it. I would say it's probably a moderate to strong linear correlation. Okay, so for A here, we're going to say moderate to strong. It's positive linear correlation. Now, again, I'm looking at that, I'm thinking it's not really a line, and from what I know from experience, it's not really a line, but mathematically, it seems to fit. Okay, let's find our correlation coefficient. So stat, calc, number 4, our lin reg, and we never have to change these things, type them all in. What do we get? Okay, well, based on this, I got a model that looks like y equals 75.64x with a b-value of 142.71. And actually, an r value of 0.927. That's pretty strong, right? That's it's a very strong model. Again, though, I know stuff about this. Okay, based on the line of best fit, part C, how many bacteria should we expect after 10 hours? Well, assuming that it kept growing linearly, it would follow this pattern, we could type this into our calculators, and we should get something like 613.69. But we know something. We know that if we look at this shape again, let's go back to the picture for a second on our graphing calculator here, that really it's making a exponential curve. We've talked about bacteria growth in past courses. A better model is exponential growth. And we know a better fit. So let's perform that nonlinear regression and find our new things. What actually makes sense? Okay, so let's get a graphing calculator back out here. What do we do with nonlinear regression? Well, lots of the same things. Let's get rid of that color there. We can go to Stat. We can go to Calc. And underneath linreg, there's a bunch of other regressions we can do. Quadratic, cubic, quartic. Notice the down arrow, there's more below. We go down below, we can find a few more. We got a ln reg, we got an xreg, we got a power regression. All these different things, a logistic. Okay, now we don't know what some of these necessarily are, but we do know what exponential looks like. So let's go to that one. Okay, again, we don't have to change anything. It's as is. Okay, at the top, it gives us our model. So a times b to the power of x, where a and b are here. And here is our r² value, our coefficient of determination. So if I was writing out the model, y equals 5.695. I have to call it 5.7. Round off to 2 decimal places. And 1.93 is my b value to the power of x. And how good is this fit? Well, it's 0.997. It's almost perfect, right? 1 would be perfect. It's pretty close to 1. And we know it's a better fit because of the shape of the data. And based on this new model, the curve of best fit, how many bacteria should we expect after 10 hours? So the same thing as part C, just using the better model, right? So let's give it a try. If we put 10 in for X, we get 4,087.41, which is a lot different than we had a 613, but probably somewhat more accurate. Now again, that's extrapolation. It's beyond the range of our data, so we shouldn't really do extrapolation, but if we had to, this would definitely be a better fit because it fits the data better, the shape of the data. And that's kind of a key. We have to think about the shape of our data. Let's try this next example. Find a regression equation with a coefficient of determination greater than 0.98 for the following set of data. Well, we got some data. Let's put in our calculators. Let's go back into Stat, Edit. I'm just going to clear this data, so I'm going to press Clear, and I'll put my new data in. Now, notice in this question that we don't have any context. It hasn't told us anything. We can't use any background knowledge to say, how is this changing? Okay, so we have to blindly try and find a regression with a coefficient of determination, r², greater than 0.98. So let's go try one. Well, what can we try? We don't want linear. Let's try quadratic. Okay, if I did a quadratic regression, what do I get? Oh, I get an r² of 0.998. That's pretty close to 1, right? That's better than 0.98. So my equation would be y equals a, just 10.5 x², b, 31.7, and c, and my r² value was 0.998. Pretty good. But what if I tried a different one? What if I tried, I don't know, a cubic function? That's the next one down. What do we get for that one? On r² value, 1 for cubic. What would the model be? Well, y equals 1x cubed, no b's, so 0 b's. C is a really weird number. It's a scientific notation by the calculator, okay? You see something like this, which would really mean 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros, and then your 2, 5. And D is 20. I got an r² of 1. Perfect fit if I use the cubic. Okay, well, if we try one more, you didn't have to pick a cubic. What if we had tried, I don't know, an exponential just for fun? See how good that one fits. Well, if I try that, another one that's over 0.98. Okay, our equation would be y equals 11.27. B is 1.65. the power of x. And we have an r squared, again r squared, remember, of 0.993. So we've tried 3 different models, all of which are basically a perfect fit. Cubic's actually a perfect fit. Which is the right one? Well, because we don't have any context, we can't really tell. That's kind of the key for nonlinear regression, is you need some context. You need to know the situation to think about the shape of your data. You could get a right answer and it still be wrong if you don't know what the shape is. If you actually look at this one, zoom number 9, it's definitely a curve, but we don't know if this curve is going to keep going up, like exponential. We don't know if it's a quadratic and it goes this way and continues on. We don't know if it's part of a cubic, goes up and then back down. We don't know, right? We just have no information. So you have to be a little bit careful when you're talking about nonlinear things to look at the context of the question. So let's look at the next one. I got some context for you again. A detector measures the amount of radioactive substance remaining as it decays. We've talked about decay before. Right? We've talked about the shape of data. But it actually tells us what we want to do in this question. We're going to create a scatter plot, then performing a quadratic regression. So let's go clear our data. Stat, edit, clear, clear. Let's enter our new data. Okay, let's create our scatter plot. And we zoom 9 it. We can see there's our scatter plots going down to the right. Okay, which means it's a curve looking at it. It's lowering. It's not quite getting as steep as we go down. We're going to perform a quadratic regression. So stat calc number 5. Let's record our equation and our coefficient determination. So y equals A, 8.43 x squared. B is 46.36 x. And C is 72.86. And our determination is 0.994. Pretty good fit, right? Almost perfect. Okay, let's repeat part B. We're going to try an exponential one this time. All right, so part B. C, same thing, but exponential. Stat, calc. Go down. Exponential is number, I think it's letter. Oh, no, number 0. Okay, let's try this one. Exponential, what do we get? Y equals, not point. We'll try 71.81. B is 0.474 to the x. And this r squared, again, make sure you're looking at r squared, is 0.998. Ooh, even better fit. Not that, really, this is not a big difference, right? It's like, if you think about percents, it's 100th of a percent. Okay. According to each model, what will be the amount of radioactive material remaining after 5 hours? So let's see what happens when x is 5. I'm going to try the quadratic one first. And if we put x is 5 in there into our equation, we get 8.43 times 5 squared, 46.36 times 5, and 72.86. And into our calculator, we should get, I got about 51.81 grams. If I try the same thing with exponential, y equals 71.81 times 0.474 to the power of 5, and this time I got 1.71 grams. And those are really different answers, right? Which one makes more sense? Which one would be more appropriate? Well, here we need to think about our context. If we go back to our picture and think about the picture and think about radioactive thing decaying and think about our past experience, we know that over time, things decay aren't going to all of a sudden start going back up like a quadratic would. They're going to continue to go down. Okay, so the exponential one makes more sense. It's more logical. And that takes us into D. Which of these two models would be more appropriate for extrapolating? Now, as we've always said, you shouldn't really extrapolate. Extrapolation is not accurate because we don't know that the data is going to continue to do what it has been doing. Okay? But assuming that's true, the shape of the data makes much more sense to do exponential. Right? And that's assuming the data continues as is. Okay? If it doesn't, well, then we shouldn't ever extrapolate. But assuming that we're going to keep decaying the way things are going, an exponential model makes the most sense. Okay, last example. The number of players required for a single elimination tennis tournament depend on the number of rounds as shown below. Create a scatter plot, perform a quadratic regression. Alright, so let's go to our calculators. Let's clear out our old data. Get rid of that curve there. Alright, so stats, edit, get rid of this stuff, and get rid of this stuff. And what do we got? 1, 2, 3, 4. And in our first round we have 2, 4, 8, 16. So not much data there, but we can still do a quadratic regression. Number 5. And our line of best fit, or sorry, our curve of best fit. Y equals 1.5 x squared minus 2.9x plus 3.5. And determination coefficient would be pretty good there, 0.998. Okay, part B, let's use this model to determine the number of players required for a 6-round tournament of this nature. Okay, so if we have 6 rounds, that means y is 6. And we'll type that into our calculators. I got 40.1 players. Okay. Seems reasonable. It's growing over time. Looks like that in the question there. But is there a better mathematical model? If I stop and look at this, it doubles again, doubles again. It seems to be doubling all the time. Well, we know that's an exponential model again. Okay? In the practical real world, lots of things follow exponential models because they grow at a certain rate and a consistent rate. So if I try this regression again, but use my exponential model, let's see how this one looks. We get y equals 1 times 2 to the x. And again, our squared value of a perfect 1, which makes sense that this is a perfect model because it is an exponential growth curve. It's doubling every single time. Okay, using our model, let's figure out how many players we need for 6 rounds this time. Okay, and again, we know this is actually the answer because it's a perfect fit. Okay, which of these is more appropriate? Part E is asking. Okay, well, obviously the exponential model is a perfect fit, both based on the r squared value, perfect fit, and what we know about how the data is shaped. That's doubling each time. That I need twice as many players for each succeeding round. Okay, that's nonlinear regression. Our homework today is on the website. It's a handout, not from the book. Give it a try. The answers are there too. If you're stuck with things, come see me. And then we'll move on to a new topic next day.